All right, so in our lesson today, this is a shorter lesson, we're going to continue to make connections between two-dimensional stuff that we already learned and three-dimensional stuff, okay? Today specifically we're dealing with the dot product and the angle between two vectors, okay? So, we've already dealt with the dot product, also known as the scalar product, okay? Make sure you would recognize it by either term, okay? It's called the dot product because we use a little dot between it. That literally is why, okay? It's called the scalar product because we're multiplying two vectors together and we end up with a scalar, okay? We end up with just a number, all right? So you guys already know how to do u dot v in two dimensions. You would take the 3, 4 dot 6, 2, and you would multiply the 3 by the 6 and get 18. You would multiply the 4 by the 2 and get an 8, and then you would add those together to get 26. A scalar. Again, that's why it's called the scalar product. Okay? In three dimensions, like a lot of the other stuff we've been dealing with in three dimensions, it's the same concept, we just have a third component to work with. Okay? So, here we are multiplying 5, 7, 11 by 4, 6, 5, and we get 20 plus 42 plus 55, which is 117. Okay? So this is nothing new. We just have a third component. Okay? So there's half the lesson right there. Okay? Seriously. All right. Part 2. What was the number one application of the dot product that we saw?
The angle between the two vectors.
Yes. Now, angle between two vectors. Now, angles in 3D are kind of a challenge, okay? We already talked about the fact that we're not going to really deal with any direction angles for one vector. And that's because there are actually 3 different angles that we could be considering. We could consider the vector's angle off of the x-axis, or off of the y-axis, or off of the z-axis. We could look at any of those angles. We're not going to do that in this class. However, this is a little different, okay? And it's going to take a little bit of remembering of geometry to understand why it's a little different, and actually why the fact that it's a little different makes it exactly the same thing that we were doing in 2 dimensions. Okay? Here's the reason. All right? In geometry, you guys learned that any 2 points form a line. Okay? Any 2 points form a line. And then, to follow that up, you figured out that any 3 points form a
Triangle.
yeah, even before triangles.
A shape. A lot. It would be
Any
a lot.
3 points?
Any 3 points form a
Circle. Angle.
plane. Thank you. You guys got it faster than 4th period. All right. So, any 3 form a plane. That's why things like the tripod are so useful, or a 3-legged stool, because no matter what angle your floor is at, or no matter, even if they make one leg a little bit short, you'll at least get a stable surface, because it's going to make a plane. If you add a 4th leg onto a chair, you got to make sure that the floor is flat and all the legs are exactly the same length, otherwise it wobbles, okay? Kind of like when you're at a restaurant, you always get the wobbly table, okay? If they just made them with 3 legs instead, they would never have to worry about wobbly tables, okay? So, here's the deal. The reason why the angle between vectors is no different in 3D than it is in 2D is because, if you think about it, we have one vector here, and we have another vector here, and what do we have? We have 1, 2, 3 points. So even though it may not be on the xy plane or the yz plane or the xz plane, it might be on a plane that's going diagonally through space, but it's still all on one plane. Okay? So we can find the angle between those two vectors using this same formula. The cosine of theta is the dot product over the product of the magnitudes. The only difference is how you're finding the dot product, like we just saw, and how you're finding the magnitudes, like we've done already. Okay? So we just looked at these two vectors and we found that the dot product was 117. We can find now the magnitude of u. Okay, the square root of 25 plus 49 plus 121. Okay. And that adds up to 195. Okay. So we have the square root of 195, which actually is simplest radical form. That's, I think it's 3 times 5 times 13. I think. Wait. Yeah, it's 39 times 5. 39 is 3 times 13. So yeah. Okay? So that's simplest radical form. We can also get the magnitude of v. We have the square root of 16 plus 36 plus 25. Okay? So that's 6177. And we just use our formula. Okay? So here, if this is our angle theta, we know that the cosine of theta is 117 over the magnitude, or the square root of 195 times the square root of 77. Okay? Same formula. By the way, those of you who didn't learn this formula last unit and just kept finding direction angles and subtracting them to get the angle between, that was a great method for last unit, but it's not going to work here. Okay? So you got to learn the formula now. Okay? Now, before we even punch this into the calculator, what do we know about theta?
It's an angle.
Cosine's positive, so theta will be positive.
It's either in the first or fourth.
Okay, if cosine's positive, it's in the first or fourth quadrant. That means, if you look at this, it's either that angle or that angle. Which one do we always use? The first quadrant angle, okay? Remember when we talk about angle between two vectors, we always do the angle between 0 and 180, okay? What happens if the cosine is 0? It's 90 degrees, okay? We have orthogonal vectors, okay? And by the way, the thing that would make them 0 is the fact that the dot product is 0, okay? And then how would we get an obtuse angle?
It would have to go all the way to, oh no, it would just be, have to be greater than 36.
No?
It'd have to be in the second quadrant.
It'd have to be in second quadrant,
So it'd be negative.
so cosine would be negative. If our dot product, that's a property we learned with in 2D, right? If the dot product is positive, we have an acute angle. The dot product is 0, it's orthogonal, so the angle is 90. If the dot product's negative, we have an obtuse angle. Okay? All right, so now that we figured that out, we know it's supposed to be acute. Let's go ahead and solve for theta. How do we solve for theta? Good, inverse cosine, or arc cosine of 117 over radical 195 times radical 77. Be careful putting in your calculator. And what do we get?
We've asked
Alright, so we got 17.29 degrees, or you could do 17.3 degrees. We do three significant figures. Okay, usually round our angles to one decimal. Okay, so again, finding the angle is the same thing. Okay, same thing we've been doing. All right. Now, here's one thing you got to be careful with. We mentioned it briefly in the last unit, but I want to revisit it here because it'll show up. All right. You got to watch out for this because sometimes we want to find an angle between two vectors, but it's after the vectors have been added together like this. Okay? That's not the angle that our formula will give us. Our formula is designed to work. It was derived using vectors that started at the same point. Okay? So notice here, if we used our formula, it would not find this angle, it would find the angle if we drew V down here, it would find that angle. Okay? So that would be the wrong angle. Okay? So there's two ways that you guys can handle this in order to use our formula still, but get the angle we're looking for. Okay? Can anyone think of one?
Yeah, you can just flip U or V.
Okay.
I mean, just flip U.
Flip U. Okay, how do we flip U? We use negative U. Okay? So we would use negative U and vector V. Okay?
Couldn't you just find the angle from the formula and then subtract it from 360?
Alright, listen to what Rebecca's saying. Think about what she's saying here. Can you say it again?
Can't you use the angle formula and then subtract your answer from 360?
What do you guys think about that?
Wouldn't it be
I
180?
don't like it.
Have a reason. Come on.
Or yeah, maybe, would it be 180?
Wouldn't it be 180? I don't remember something on the test that wasn't working out because I was subtracting from 360. I meant to ask you about that, and it was like it didn't make sense because it was giving me something that was in the third vector, and all the other forces were pointing the other direction. And then I did it from 180. It worked. So
Okay.
I'm not sure why.
So you just went with it.
I don't know why it's 180. But I
Okay.
think it should be.
What do you guys think about that? Subtract, get the angle using U and V, but then subtract from
180.
180?
That's not good.
Because isn't that the same thing? Like V minus U?
V minus U, well,
Oh, never mind.
yeah, we're not, that isn't a plus sign, that's just and. Okay,
That's
come on, think guys, what do you think?
Is it not 180?
She's saying use vector U and vector V, but then subtract your answer from 180 degrees. Will that work?
I think so. Yeah. That's
Yeah,
what I
because
would.
like if theta was 5 and then you moved it down,
No, I'm doing
because it would be a transversal, so
It would work because
Keep going, keep going.
it's parallel. So like if you drew the line from the
So we're saying draw V down here like we had it earlier.
Mr. Erickson, I have a question.
Okay,
yeah.
let's keep going with this for a sec, I'll come back, okay? And you said that these would be parallel. Are these parallel?
Yeah.
Yeah, they're the same vector, we just moved it, right? So that's vector V.
it's
So-
transversal.
So yeah, vector U is acting as a transversal here. So what do we know about this angle and this angle?
So theta, it's 180 minus theta.
They're supplementary. Those are same side interior angles. If this is a transversal and we have two parallel lines, Remember our geometry?
Yeah.
Okay, then these add up to 180. So if that's theta, this is going to be 180 minus theta. Okay? So, that is right. Okay? If you use u and v when they're added together like this, you're going to get the supplement of the angle you're looking for, not the angle. So just subtract it from 180 and you've got it. Okay? What was your question, Evan?
No, I was gonna ask the same thing, cause I was gonna ask like, if there's a rule about like quadrilaterals, all the angles like adding up to 360, right?
Mm-hmm.
So that's what I was gonna say, since we have like two angles of the quadrilateral, it would be 180 instead of 360.
Yeah, that's kind of like, if you remember we did that parallelogram method of adding.
Yeah.
If we added this and added this, we'd have a parallelogram. And yeah, these two angles would add up to 180 that way as well. Yeah. Ahmad, were you going to say something earlier? No? You sure? Okay. All right. So here's two ways that you can handle this. All right?
One of them you could just do the regular thing with negative u and v.
Mm-hmm.
The other one you could do u and v but subtract from 180.
Yeah.
Oh.
So either way, you've got to throw a negative in there if you think about it, okay? You're either subtracting it from 180 or you're making the one vector negative from the get-go and then what you get is what you get. Yeah. Yeah. Ken?
This will both work in all cases, right?
Yes, these will both work in all cases. All right. If you have two vectors added together. So think about it like this. You remember when we had the airplane flying and then the wind was blowing? If we wanted to find the angle between where the plane was trying to go and the way the wind was blowing, we can find that angle using this formula. Okay?
So we would say, for example, we do the negative u plus v. We would put that into as the dot product in that formula, or
You would do the dot product of negative u dot not dot v. Negative u dot v. Okay? All right. Actually, let's think about that for a second. You're doing negative u, catch up, dot v. Okay? And this actually ties with what we were doing, or what I want to look at next here real quick. Remember the properties of the dot product? When you have a constant times a vector, that's negative u, negative 1 times u. Remember, you can put that constant wherever you want, really. So we could pull that negative out here and do u dot v. Think about that with our cosine. When cosine was positive, we're first quadrant. Making it negative would give us the same reference angle, but in the second quadrant, i.e. the supplementary angle. Okay? So that's why this will work either way here. Okay? So, now that ties us to this. I wanted to remind you of this. I actually just copied from a previous lesson in last unit here when we looked at properties for vectors. Okay? When we have vectors and we're looking at the dot product is commutative. That still applies here with 3D. The dot product of something with itself equals the magnitude squared. That still applies here in 3D. Here's what we just looked at. We had the negative, like that k was the negative 1. Okay? You could pull the negative 1 out in front, or any constant. Do the dot product first, and then multiply it. Okay? And then also we had this distributive property. If you have vector addition, and then you're dotting that with another vector, you can distribute and do the two dot products first, then add the numbers together rather than adding vectors together. Okay? That still applies in 3D. Okay? So, that's it. Alright, the rest of our time, I want to use letting you guys practice using some of this stuff. Okay? Finding dot products, finding angles between vectors. Okay, if you go to the go to the required IP for this day. You could practice with some of these. You could work in small groups and but make good use of this time. Okay?
Minutes left.
All right.